All right, we're going to continue our discussion about epoxides. We've learned that one of the common ways of making epoxides is from an alkene plus a peroxy acid. The most common peroxy acid that we talked about was MCPBA, stands for metachloroperibenzoic acid. We'll talk more about the naming of that when we get to the aromatic chapter, but that's the most common peroxy acid that is used in order to make the epoxide. And the reaction can't be done in water or any type of an acid, because we've learned that you can open up these epoxides in the presence of acid or water, which we will talk about pretty soon. So that's one way of making the epoxide. The other way is a halohydrin. This is an intramolecular SN2 reaction. Intramolecular meaning the same molecule, SN2. You can see right here that your O minus kind of closes up onto itself, making a ring, three-membered ring, in this case an epoxide, and kicking out your halogen. So remember, halohydrin is where you have an OH and a halogen on the same molecule, and they have to be at the 1 and the 2 carbons. They have to be 2 carbons from each other. It's not like they're on the same carbon, or one's on one carbon, one's on a different carbon. They're right next to each other. Okay, so halohydrin. Okay, add some sort of base, pluck off the hydrogen, form the O minus, do the SN2 attack to form the epoxide. All right, so those are the two main ways of making them. This is just kind of a review of how to make the halohydrin. It comes from a double bond with water and the halogen. All right, so if you add any halogen plus water, you get the halohydrin compound. All right, and they're always trans. All right, remember, if you did this reaction without the water, if you just had the halogen, you would get a chlorine here. So you'd have a dichloro compound. But in the presence of water, we learned you get the halohydrin. Once you have the halohydrin, now you can add the base to it and make the epoxide. This is a 2-step process. So the other way is MCPBA. That's just a 1-step, but sometimes MCPBA doesn't work. So here's just another way of doing it. All right, now sections 12, 13, and 14 are about the opening of epoxides. All right, the first way is in the presence of acid and water. All right, acid is a catalyst. The acid protonates your oxygen. All right. We've talked about these. You're going to see this a lot this semester, is where oxygens get protonated to form a plus charge. In this case, you have a very strained ring plus an oxygen with a positive charge on it. So this oxygen wants to break a bond. All right, all it needs is something, some sort of nucleophile to come in here, start into this carbon, and pop and break that bond, put those electrons on the oxygen, and pop the OH open. All right. So in this case, you have water attack from underneath. That's why you get the transdiol, and it pops it open. So this OH here is the same as this OH. Let's actually color this in. So this oxygen right here is the same as this oxygen right here. All right. So it just kind of pops open, and then you have water come by, pluck off this hydrogen to form your product, plus to regenerate acid. So water comes in, plucks off that hydrogen, gives you the OH plus H3O plus, which is what you start out as your catalyst. Right? And you remember, you get the transdiol. Right? Now, what would happen if you did the same thing, but rather than in water, you were in alcohol? Well, mechanism's identical. Instead of getting a transdiol, you would actually form a hydroxy ether. Okay, hydroxy ether because a hydroxy group in an ether, but you have a methoxycyclopentanol. So you have both an alcohol and an ether type of group. Same mechanism. You protonate. Okay, get the string ring. The oxygen from your alcohol comes in and attacks, pops it open, and then you have water come by and pluck off the hydrogen, and to pretty much reform your acid. Okay, so this is exactly the same thing as the last mechanism, but rather than having H here, you have an R group there. Okay, so now here are the words. A molecule of alcohol acts as a nucleophile rather than a water to open up the epoxide. And in this case, you get what's called an alkoxy alcohol. I called it a hydroxy ether. It really doesn't matter how you call it. All right, here's kind of a hint. Your book kind of does this. I kind of like this. In proposing mechanisms for acid-catalyzed opening of an epoxide, imagine that the protonated epoxide opens to the more stable or the more substituted carbocation. All right, so always remember if you're forming, in this case we're not forming carbocations, okay, but that's kind of where our nucleophile is going to. It's going to the more stable position, okay, and you see it much more when you have a base-catalyzed opening epoxides. Last part was acid-catalyzed. This is now base-catalyzed. So we no longer we're not protonating the oxygen in this case. In this case, we're just adding to it and popping it open. Okay, so rather than having water and acid come in, we're having hydroxide come in. Now, you'll see, you can imagine, what if you had an R group here instead? What if you had an R group? You would get the same thing, an OH with an OR group. Now, the thing about the base ones is our second step, I have to add acid to it to protonate the O- to get the H. Okay, but the hydroxide ion attacks and opens up. A diol is attained after protonation of the alkoxide with water. So our next step, so here's actually a two-step process. I actually have to add in a second step where I actually add acid so that your negative charge can protonate itself to form a diol. Okay. So ring opening with hydrohalic acids. Well, okay, fancy names for basically HCl, HBr, HI. Okay. This is kind of interesting. So you have to be very careful as to what kind of acid you use. Okay. In this case, if I have an epoxide plus, let's say, HCl, all right, you protonate, you get the halohydrin. But then if you keep adding more HX, all right, you're going to actually get rid of your OH and place it in X. So after protonation of the halide ion attacks to protonated epoxide, which is this, the hydrohalide initially formed reacts further with HX to give 1,2-dihalide. Okay, so that's kind of a side reaction that you have to be careful of. Now let's talk about regioselectivity of epoxide. Here's where we're talking about forming the more stable compound. All right, in the presence of acid, so this is very important to note. All right, we'll talk more about this in class. Notice I have a unsymmetrical epoxide, meaning on one carbon I have one group or two different groups than I do on the other carbon. So they definitely are different sides. Okay, in the presence of acid, all right, your nucleophile goes to the more substituted position. So in acid, if we're in acid, the nucleophile goes to the more substituted. If we don't have acid, if we just have O negative, now ETOH is ethanol. This is just the solvent that this reaction is done in. Okay, it's not actually part of the mechanism. Okay, so here I just have a O negative. All right, this group, all right, goes to the least substituted. Okay, so notice in the presence of acid, this oxygen, we'll kind of see. I'll kind of draw a mechanism on the next page. This oxygen goes to that carbon because it's more substituted. I got methyls rather than hydrogens. In the O- case, okay, the O- goes to the least substituted carbon. Okay, that's what's meant by regioselectivity. What region is it going to? So you have a blank page. Let's kind of do this mechanism. Okay, so I'll kind of show you why this happens. So CH3, O, CH3. Oh, no, sorry. Let's erase that. I need a carbon there. CH3, carbon, CH3, epoxide. And then this is a CH2. All right, let's do it first with the O-, because that's the easiest one to explain first. Okay, so the O- has two positions. It can either attack the carbon here, or it can attack the carbon here. Now this is a pseudo SN2 type of mechanism. Okay, it's SN2-like. I'll put in quotes because it's not really an SN2, but it's like an SN2. Now, SN2s, strong nucleophile, and what do they prefer? More substituted or least substituted? All right, hopefully you're saying least substituted. All right, because you have a strong nucleophile, it wants to go to the less sterically hindered position. All right, because you have all these carbons. This has to sneak in here and hit either bond to a carbon with 2 hydrogens around it, or do you think it's going to want to bond with a carbon with 2 methyl groups around it? All right. Now, I don't form any intermediates. This is a concerted reaction. It wants to go to the less sterically hindered. So this is going to go to this carbon right here and pop open your epoxide. Okay, to form CH2 plus your new group that you just added to it. Okay, Lee substituted. Then obviously our next step is to add acid to it to protonate. Okay, I'm not going to draw, I don't have room there. Okay, so in base, it goes to the least substituted. That's what we said right here. If you have an O minus, it goes to the least substituted, because remember, this is SN2-like. Okay? Now, in the presence of an acid, what happens? Okay? Well, in this case, in the presence of an acid, you have kind of this carbocation formation. Okay? So the first step is you protonate. Okay? You protonated. Okay? Now that we protonated, we have, I'm going to change pointers here. Now that we protonated, remember I have this bond here, and I have this bond here. Okay? Now, these bonds want to break. They really want to break. Why do they want to break? It's strained, plus my oxygen wants electrons, wants lone pairs. Okay? So what starts happening is one of these bonds actually starts breaking before a nucleophile comes in here. And the question is, which bond do you think is going to want to start breaking? All right, do you think it's equal, or do you think one wants to break more than the other? Well, obviously, since I have regioselectivity, one of these bonds is going to want to break more. Okay, which one is it? Well, if my nucleophile attaches to this carbon, then obviously this is the bond that wants to break more. And why is that? The reason is because, remember, I have a partial positive on this carbon, and I have a partial positive on this carbon. But these partial positives are not equal. Okay? The reason is because this carbon, if it were to form a carbocation, would be a tertiary carbocation. This would be a primary carbocation. So which carbocation is more stable? The tertiary. So this bond is the bond that's already kind of breaking. I'm going to kind of exaggerate this molecule over here. This is kind of what this molecule looks like. You have kind of a very weak bond with an oxygen. It's not completely broken. Okay, they haven't proven that it's broken. And I have a bond right here. I'm going to make it darker because that's actually a bond right there. Okay, with my plus charge. This is weakly bonded. Why? Because I have this is a much larger partial positive than this one. See how small of a partial positive that is? Okay, this is so much more partial positive because it's kind of making a tertiary. Notice I have 3 carbons around it. Okay, it's a tertiary carbocation opposed to a primary carbocation. So because when I protonate this bond already starts breaking. This is a much bigger positive charge. So my nucleophile now, which I believe is the alcohol, is ethanol. All right. These lone pairs, this negative is going to be more attracted to the more partial positive carbon than it is to the least partial positive carbon. So that's why it's going to want to attack the more substituted position, because you kind of are forming this very large partial positive or tertiary carbocation. All right. So in the base mechanism, it's based on, no pun intended, it's based on sterics. Okay? In the acid-catalyzed reaction is based on carbocation stability. Carbocation stability. Okay? So that's why you get this regioselectivity here. In the presence of the acid, it protonates, it starts breaking this bond, making this tertiary carbon much more partial positive, so it can come in and attack. In this case, it's the exact opposite. Okay.